It is my great pleasure to introduce John and Brandon from Keysight Technologies.
Hello, I'm Brennan Postlethwaite. I'm currently a product support specialist at Keysight Technologies. I specialize in wireless electrical engineering. I've been doing this for about 15 years. I started as an Air Force radio satellite maintenance technician. So I've gone from doing that to a litany of other things. I'm just going to give you a quick show of some of the things I've worked on. So for my screen here, you can see this is a portable satellite terminal that we would use to link up troops in the field and get them emergency messages. And I've also worked on your classic handheld radios. And one of the more recent things before I was at Keysight was I worked on handheld Wi-Fi checkers. So I've been working on wireless and radio communications and cell phone communications pretty much my entire professional life. Now that I'm working at Keysight, I'm working on our most advanced radio technology network analyzers. I work with John Grubb. John?
Yeah, hi, this is John, and I had a little more traditional path to becoming an electrical engineer. After high school, I had always been interested in math and science and physics, and I was looking for a career. I decided I wanted to be an engineer and settled on electrical engineering as a choice. I grew up in the Midwest, so I went to the University of Michigan in Ann Arbor, which is right over by Detroit, and graduated with a bachelor's in electrical engineering. And I had a concentration in communication systems while I was there, and was hired actually by HP here in Sonoma County in 1981. So I've been in Sonoma County working at HP and was Agilent for a while now, Keysight Technologies for 39 years. So I've had a variety of jobs there, software engineering, hardware engineering, and I manage a team of engineers at this point. But yeah, I really love working there. It's been a great place to work, and the technology is terrific. Lately, the move towards wireless devices and connectivity is just everywhere and becoming more and more prevalent. So it's a great place to be.
So as you can tell, our primary focus is on radio waves. And to cover some of the basics of radio waves, I've got a few simple demonstrations here. So once again, share. So is that showing up, John?
Yes.
Yes. So what I have here is I've got a three-dimensional graph, and it's showing up the wrong size, so we'll just adjust that. So I have amplitude, which is to say how much power the signal has, frequency, as in how fast the signal changes, and then time, which is a measurement, of course, of the signal over time. So I'm going to start this basic signal oscillating. And any radio signal is just a change from one voltage to another, most often from a very positive to a very negative one, and that allows it to radiate off of an electrical element. So as you can see here, the size of the signal, even though it is rotating, oh, it has broken. The size of the signal is the same, but the voltage value changes. And these interact with each other. So I can add or reduce elements. And you can see that the time graph gets much more complex. But in reality, it's just this slow signal and a few faster frequency signals combined together. So these are, in this case, electrical signals, and electricity tends to want to travel at the speed of light as fast as it can through whatever it can. And this is the basis for every kind of radio communication you've got: cell phones, handheld radios, pagers, your Wi-Fi. Everything works on these principles, just at different frequencies and different modes. So here's an example of how that signal would travel down a metal transmission line, so a cable up to your cable modem or a cable up to an antenna. You can see the wave moves. This is moving at the speed of light, just slowed down for our demonstration purposes. And then it reaches the load, and the load handles the signal. It's either an antenna sending the signal out to space, or it's the device processing the signal, all of those. So given that, we have a device, and I'll show it to you. Am I back on camera? No, I'm not. There we go. Okay. We have devices like this. And is my video working, John? It's showing frozen on my end.
It's not showing yet.
There we
Oh,
go.
there it is.
It
Okay.
took a moment to catch up. So this is a handheld signal analyzer. This is capable of receiving very complex signals and providing measurements and other information on them. And we can use this to make sure that all of those devices that I've listed are working appropriately, that they do have the right frequency, the right power, and that they are reaching where they need to reach. So if say your cell phone can't reach the tower, I could hook this up to the tower's antenna system and see that the signals are reaching it. So I actually have a few simple demonstrations set up on that front. And the first one is, of course, your standard cell phone. So I'm going to go back to sharing my screen again, and you're going to see I've remoted into that device. So dead center here. And what I have here is a measurement of several cell phone bands from 1.7 gigahertz to 2.16 gigahertz. And that's a billion cycles for giga. So that's saying that at this frequency, all the signals right where my mouse icon is oscillating at 1.7 billion times a second. And it's measuring how much power is happening at that speed. And at the top end here is 2.16 billion times a second as a frequency. If there's any energy there, it'll be reported. So right now you can see there's just noise. This is very low power. But if I take a cell phone and I make a phone call near this device, so I will call my voicemail, give it a moment to call out, you can actually see and measure my call and see what frequency it is, how much power it has, and a few other aspects about that call. And if I end the call, the signal vanishes. You can also take other kinds of measurements. You can make other inferments. As you saw, it was a very narrow peak. There wasn't a lot of what we like to call bandwidth. It's only using a few frequencies. So if I have another demonstration of Wi-Fi. So now I'm in the Wi-Fi bands. And the Wi-Fi bands, of course, are going to be very busy. I live in an apartment complex, so everyone's using Wi-Fi all the time. And in fact, you can see tiny spikes of activity at different channels. But if I, again, take my cell phone and I load up something that's going to use a lot of Wi-Fi data, like a YouTube video, you can see that activity speeds up a lot. There's a lot more requests for data going between my router and my cell phone. And I will actually turn up the quality so you can see a lot more spikes there. And you see how this is wider than that narrow peak. That's because there's more data being sent across more frequencies at once. And that's what we call bandwidth, is it's taking up more of the band, but it's able to send more data because it's using more frequencies. Turn my video back on. So in the end, all of these are just standard radio behaviors. Your cell phone is just a pack of multiple radios. And our devices help you measure and test them to make sure that they're functioning okay. And they test and measure your router, and your cell phone tower. So we have to develop technology that actually can measure all of these generically and understand them so that we know that they're doing what they need to be doing. John, do you want to cover what we do at the handheld side?
I can talk a little bit more about how this kind of a device might be applied in a real world situation.
That sounds awesome.
So um, when large events occur, like say the Olympics or World Cup, or say a race of some sort, sporting events, large crowds of people come together, massive amounts of radio infrastructure goes into place. You can imagine, if you think about it, take the Olympics. You've got thousands of athletes coming around. They're all posting to Instagram over some Wi-Fi network. They're making international phone calls. You've got highly secure environments where there's security talking on handsets going back and forth. You've got TV crews everywhere. They all have satellite uplinks and they're all communicating to different countries around the world. So there's this massive radio infrastructure that goes into place in order to put on an event like this. Those signals that Brandon was showing on the screen can interfere with each other. And when that infrastructure goes into place, they would use these devices to verify that that everything's working correctly and as expected, that when some sort of security situation occurs, they're not going to get interfered with when somebody's like posting to Facebook. And so these are very real live situations that occur, that these devices are used for. And so customers buy these, and it can be as straightforward as Verizon putting in a cell tower and then verifying that that cell tower is working, to much more complicated situation like I was just describing. So they're very widely applicable devices, and becoming more and more necessary as infrastructure goes into place.
And Stefan is asking, how can radio frequencies interfere with one another and what are the effects? Well, the most obvious one is you can only have a certain amount of energy on a frequency, and if someone else is putting out at the same frequency, you are going to jam each other out, because that nicely oscillating signal will suddenly seem like a constant signal, or it will become distorted. Another thing that can happen is mixing, where you have two frequencies that are separate in frequency, but they hit a device where they both make that device resonate, or they both change their frequency as they hit a device, and they come out on the same frequency, and we call it intermodulation. So you want to keep your transmissions in just the frequencies they're intended for. And you can actually notice this. There are several applications available for cell phones that do what is called a Wi-Fi site survey. And you can use these to see how many different Wi-Fi access points are in an area. And especially in apartment complexes, you'll see a lot of people set up their Wi-Fi on the same channel, and they'll have trouble getting their Wi-Fi to work very well because everyone's in that channel. They do. The question is, do radio frequencies have the ability to pass through certain materials? If so, does the frequency's length change its property? It does. And this is, we'll get to you in just a moment, Carrie. So higher frequencies have less capability of penetrating material because they need to be able to oscillate freely. So as you get up into the Wi-Fi and the gigahertz range, you can't penetrate walls and metal as easily as you can with your UHF or cell phone radio frequencies, which are lower but higher power. Future of radio usage? No, radio. When I say radio, I'm not talking about like your handheld walkie-talkie like what I have here. Radio is a physical phenomenon. It's a property of physics. In order to get a signal to move freely through space from some piece of electronics to another, you have to use radiation. You have to use electromagnetic radiation. So you will always have some form of analog sine wave electrical propagation in order to send signals. And all the newer technologies like 5G, LTE, or WiMAX, all of those are just more refined versions of radio technology. They're more precise. They're better able to handle high frequencies. They're better able to take weak signals and catch them through the noise.
We also have a question from Carrie. Have you always been interested in this? If not, how did you find out that you wanted to do this as a career?
So that one's kind of amusing. So I mentioned I started in the Air Force, and I thought I was going to go into server maintenance, DevOps, something to do with the software side of computers. And at the time, that I didn't have a driver's license. I was fresh out of high school, and I just didn't have an opportunity to get a driver's license. And that was one of the requirements, is for that job you had to have a driver's license. But I'd scored very highly on my electronics aptitude. So instead they said, well, you could do radio or satellite. And I was actually a bit put out because I thought, wow, radio and satellite is old technology, kind of like Carrie's question. It's like, that's not cool anymore. But as I got into it, I realized it is still in use and it is cool, and they're doing very neat stuff to make it better and faster. But also, it's kind of the truth. Like, you can put any kind of software, I mean, like this Zoom meeting is just software. And in the end, you have to be able to get that to physically go out somewhere. And all of that physics comes from the hardware. And that's where I became very interested, was that you can do anything with software, but hardware has to deal with physics, and radio physics are the most interesting of all electronics physics. The most interesting part. So Stefan has a question here. What was the most interesting piece of equipment did I work on in the United States Air Force? So I could not find a good picture of this, but there's a delightful radio called the RT1446. And it's a pretty normal radio. You can do Morse, you can do voice, you can do data. But what's cool is that it works in a special frequency band called HF, high frequency. And it bounces off the ionosphere and off the surface of the Earth, so that you can use it to communicate globally without needing any kind of satellites or special equipment. So it was really neat to be able to take this thing, set this thing up out in a field in the middle of Missouri, and as long as I had a proper antenna, I could speak to anyone in the world with this thing. And Seraphim has a question, is Bluetooth a type of frequency? Bluetooth is a standard. So Bluetooth is a definition of protocols, as in how it communicates, frequencies, what frequencies it uses, and data formats. So Bluetooth has frequency ranges, and you can actually look those up. In fact, there are different grades of Bluetooth standard now. They've upgraded. But yes, it has its own radio frequencies as well. But it's more than that as well. It's also a set of rules for how you use those frequencies to communicate.
We also have a question about, have you assisted with any new product launches? If so, what was your personal input in the product?
So the one I held up was actually one that John and I worked together to launch. John, would you like to field this one?
Sure. So developing a product like this is pretty complicated effort. It takes usually from 5 to 20 engineers to develop this over the course of 18 to 24 months. So the product launch starts with customer needs. And so say, for instance, today, the marketing organization is looking at what 5G requirements are being asked for. And those requirements feed the definition of the product. There's a definition that gets created, and then the product is designed. During the design process, we go through a series of qualifications to determine the performance of the hardware, and then ultimately come up with a data sheet for that hardware that the customer uses to buy with, because they know their requirements and they can compare that data sheet to their requirements. So that qualification process is one that both Brandon and I have been involved with, and is pretty extensive because we're selling measuring devices. The accuracy of the measurements is paramount. So the exercise of verifying the performance of the electronics is fairly extensive and goes on for a number of months, and ultimately results in a product. At some point, we may actually even do qualification testing, like dropping it. So the product that Brandon was showing has, I think we have one at work that was dropped from a cell tower. It's actually still works. And, things they fall off the back of a truck, or you name it, so these are all things that have to be verified that they're going to be okay before we actually ship a product.
We have some very amazing physical tests as well as electrical tests that we put these through. It's a lot of fun to try and break them.
Yeah, so if you think about what it takes to do this sort of thing, we have everything from packaging engineers who create the boxes to mechanical engineers that are designing the rubber feet and the thermal aspects, temperature pieces, so the electronics, and then the technicians and the assemblers and the production team and the materials team that does all the purchasing of all the parts. So it takes a very large team to create a product like this and introduce it. There's a lot of different specialized skills that go into it.
Brandon, could you tell us a little bit about being an amateur radio operator? What's cool about it, and how might it help during an emergency?
Yes, so I neglected to mention my introduction. I'm a licensed amateur radio operator, or as they call it, ham radio. And it's kind of a hobby that's splintered off from my career. It came from being interested in wireless electronics. It's very cool because it lets me connect in different ways and lets me practice at home with different technology. As you saw, I've got my personal handheld radio. I also have several desktop radios set up in my home lab, some of them capable of very different frequencies. And I'm working on getting ARES certified, which is an amateur radio emergency service, which means that, like right now we have the glass fire going, I can be activated to help provide communications support. So for example, if they need someone to be a radio operator for the fire department, or if they need a forward operations base and they need someone sitting at the radios, I can help coordinate with that. It's also a great way to just practice. It gives me privileges to use certain frequencies that the FCC says you have to have a license for. And those frequencies are really good compared to publicly available ones. They propagate better, or they offer more data bandwidth, and allows me to test, like I can build my own antennas and see how good those antennas are. Or I can do what's called contesting, and people can say, okay, between Monday and Friday, reach as many people in the United States with ham radio as you can, and we'll all go out and try and contact each other using our equipment and try and test how good our equipment is set up.
Could you tell us how a student could learn more about becoming a radio operator?
Certainly. So Amateur radio, we actually have an active club, the Sonoma County Radio Amateurs, and they provide resources for both teaching and licensing people. And they even have some loaner equipment, I believe. So when you do get licensed, you can borrow a radio until you get your own. There's the Amateur Radio Relay League, which is the big umbrella organization for ham radio operators, and they provide testing materials, information. They host contests. They have seminars and meetings on how to make antennas or how to choose radios, and they'll even discuss different modes and such.
I was wondering, Brandon, if you could talk a little bit about the worksheet and what we're going to be doing in the breakout rooms.
Certainly. So, what I've given are a few very basic problems, but they don't look like it at first. And what's happening is you're dealing with the speed of light, which is exceedingly fast. And the speed of light in a vacuum is about 300, is it million meters per second? And when you get into air, it's slowed down a little. And when you get into metal, when you're trying to send a signal down a copper wire, it's even slower than that. And what you're looking for is if a signal is oscillating, as I showed in the diagram, from here and it's oscillating to here, how much time does it take to get between those 2 points if it's going at the speed of light? And that becomes your measure of wavelength. And that becomes important because you need an entire wave to be contained on an antenna, or you need it to be contained within your cable so that it doesn't radiate or it does radiate how you expect it to.
When I was looking up my cell phone frequency, there were a number of different frequencies for my cell phone carrier. So, should students just pick one of those?
Yes, just pick any one. Your phone is capable of tons upon tons of bands, and that's both a factor of how advanced the radios are becoming and that they can receive all these frequencies, but also necessity because again, cell phone manufacturers don't want the bands to interfere. And as more and more people are using cell phones and they're using more data on wider bands on those cell phones, we're running out of space. So your cell phone has to be more capable, but also the cell phone towers have to be more capable. So your phone is going to be capable of a very wide range of bands. For the worksheet, I would just pick one. I would definitely recommend one of the even numbered bands, something that's a nice stable frequency so that the math's a little easier.
Did you follow the story where the vintage television set was crashing the village Wi-Fi?
I did not.
Do you know why that might occur?
Absolutely. So old CRTs are, again, oscillating devices. And the way they draw, instead of having pixels on a grid on a screen that you turn on and off, they are sending a sweep back and forth, and my camera's not fast enough to catch this. They're sending a sweep back and forth with differing color information and brightness across the screen. And as they're doing that, it has frequency. And if that frequency is the same, or if it is what's called a harmonic of the Wi-Fi, it can radiate from that TV and interfere.
So this was in Wales, and the Wi-Fi was out in the town for 18 months. And so how would they fix that? Would a Keysight instrument help diagnose that problem?
Absolutely. What you would do is, so if you look at my device again, what I have on here is what we call a monopole or a rubber duck antenna. It receives every signal from every direction equally well. Well, there are also directional antennas. They look like your classic TV antennas where they've got a bunch of spokes sticking out and they look kind of like a triangle in one direction. And those antennas receive better in one direction than in another. And you can use those to play a game of hot and cold and point them this way. Okay, the signal got weaker. Point them this way. The signal got stronger. The signal's in that direction. And you could hunt down that TV and find that it's causing the interference.
Cool. Well, I think we are ready to go into breakout rooms.